Memory management. Memory is an important resource that must be carefully managed. While the average home computer nowadays has 2,000 times as much memory as the IBM 7094, the largest computer in the world in the early 1960s. Programs and the data they are expected to handle have also grown tremendously. The paraphrase Parkinson slow programs and their data expand to fill the memory available to Holland. In this chapter, we will study how operating system manage memory. Ideally, what every programmer will like is an infinitely large, infinitely fast memory that is also non-volatile. That is, does not lose its content when the electric power fails. While we are at it, we now also ask for it to be expensive too. Unfortunately, technology cannot turn such strings into memories. Consequently, most computers have a memory hierarchy with a small amount of very fast, expensive, volatile CAC memory, hundreds of megabytes of medium speed, medium price, volatile main memory, RAM, and 10 or hundreds of gigabytes of slow, cheap, non-volatile. This storage is the job of the operating system to coordinating how these memory are used. A part of the operating system that manages the memory hierarchy is usually called the memory manager. Its job is to keep track of which parts of memory are in use and which parts are not in use, to allocate memory to process when they need it and delocate it when they are done, and to manage swapping between memory and disk when main memory is too small to hold all the process. In most systems, but not ministry, is the inner kernel. In this chapter, we will investigate a number of different memory management schemes, ranging from very simple to highly sophisticated. We will start at the beginning and look first at the simplest possible memory management system and then gradually progress to more and more elaborate ones. As we point out in Chapter 1, the story tends to repeat itself in the computer world. Mini computer software was initially like mainframe software and personal computer software was initially like mini computer software. The cycle is now repeating itself with plain-top PDAs and embedded systems. In these systems, simple memory management schemes are still in use. For this reason, they are still worth studying. Basic memory management. Memory management system can be divided into two basic classes. Those that move process back and forth between main memory and disk during execution, swapping and paging, and those that do not. The latter are simpler, so we will study them first. Later in the chapter, we will examine swapping and paging. Throughout this chapter, the reader should keep in mind that swapping and paging are large artifacts caused by the lack of sufficient main memory to hold all programs and data at once. If main memory ever gets so large that there is a churn enough of it, the argument in favor of one kind of memory management scheme or another may become obsolete. On the other hand, as mentioned above, software seems to grow as fast as memory, so efficient memory management may always be needed. In the 1980s, there were many universities that ran a time-sharing system with thousands of more or less certified use on a 4 MB VAS. Now, Microsoft e-commerce have been at least 120 MB for single use. Windows type system. The trend toward multimedia put even more demands on memory, so good memory management is probably going to be needed for the next decade at least. Monoprogramming without swapping or paging. The simplest possible memory management scheme is to run just one program at a time. Train the memory between that program and the operating system. Three variations on this theme are shown in Fig 4.1. The operating system may be at the bottom of memory in RAM, random access memory, as shown in Fig 4.1a, or it may be in ROM read-only memory at the top of memory, as shown in Fig 4.1b, or the device drivers may be at the top of memory in ROM, and the rest of the system in RAM down below, as shown in Fig 4.1c. The first model was formerly used on mainframes and mini-computers, but it rarely used anymore. The second model is used on some home-top computer and embedded systems. The third model was used by early personal computers running MS-DOS, where the portion of the system in the ROM is called the BIOS, Basic Input-Output System. When the system is organized in this way, only one process at a time can be running. As soon as the user types a command, the operating system copies the request program from disk to memory and executes it. When the process finishes, the operating system displays a prompt character and waits for a new command. When it receives the command, it loads a new program into memory, overwriting with the first one. Multi-programming with phase partitions is based on very simple embedded systems. Monoprogramming is hardly used anymore. Most modern systems allow multiple processes to run at the same time. Having multiple processes running at once means that when one process is blocked waiting for I/O to finish, another one can use the CPU. Such multi-programming increases the CPU utilization. Network servers always have the ability to running multiple processes for different settings at the same time, but most silent desktop machines also have this ability nowadays. The easiest way to achieve multiprogramming is simple to divide memory arm into n possibly unequal partition. This partitioning can, for example, be done majorly when the system is start up. When a job arrives, it can be put into the input curve for the smallest partition large enough to hold it. Since the partitions are fixed in the scheme, any space in partition not used by a job is waste while that job runs. In phase 428, we see how this system of fixed partition and separate input curves looks. The disadvantage of sorting the incoming job into separate curve becomes apparent. When the curve for a large partition is empty but the curve for a small partition is full, as is the case for partition 1 and 3 in Fig 428. Here small jobs have to wait to go into memory, even though plenty of memory is free. An alternative organization is to maintain a single query as in Fig 42b. Whenever a partition becomes free, a job close to the front of the query that fits in could be loaded into an empty partition and run. Since it is unsuitable to waste a large partition on a small job, a different strategy is search the whole input curve whenever a partition becomes free and pick the large job that fits. Note the latter algorithm discriminates against small jobs as being unworthy of having a whole partition, whereas usually it is desirable to give the smallest job often interactive job the best service. In other words, one way out is to have at least one small partition around. Such partition will allow small jobs to run without having to allocate a large partition for them. Another approach is to have a rule stating that a job that is eligible to run may not be skipping over more than k times. Each time it is skipped over, it gets 1 point. When it has acquired k points, it may not be skipped again. This system with phase partition set up by the operator in the morning and not changed thereafter was used by OS 316 on large IBM mainframes for many years. It was called MFT, multiprogramming with a fixed number of tests of OS MFT. It is simple to understand and equally simple to implement. Incoming jobs are called until a suitable partition is available, at which time the job is loaded into that partition and run until it terminates. However, nowadays, few, if any, operating system support the model, even on mainframe batch system. Multiprogramming introduces two essential problems that must be solved: relocation and protection. Look at Fig 42. From the figure, it is clear that different jobs will be run at different edges. When a program is linked, the main program uses written produce and library produce are combined into a single edge space. The linker must know at what address the program will begin in memory. For example, suppose that the first instruction is a call to produce a bullet address 100 within a binary file produced by the linker. If the programming is loaded in partition 1, an address 100K, that instruction will jump to absolute address 100, which is inside the operating system. What is needed is a call to 100K plus 100. If the program is loaded into partition 2, it must be carried out as a call to 200K plus 100, and so on. This problem is known as the relocation problem. One possible solution is to actually modify the instruction as the program is loaded into memory. Programs loaded into partition 1 have 100K added to each address. Programs loaded into partition 2 have 200K added to addresses, and so forth. To perform relocation during loading like this, the linker must include in the binary program a list or bitmap telling which programming words are asked to be relocated and which are upcode constants or other items that must not be relocated. OSMFT worked with this way. Relocation during loading does not solve the protection problem. A malicious program can always construct a new instruction to jump to it, because becoming in this system use absolute memory address rather than address relative to a register. There is no way to stop a program from building an instruction that reads or writes any words in memory. In multi-user systems, it is highly unservable to reprocess read and write memory belonging to other users. The solution that NBM chose for protecting the 360 was to divide memory into blocks of 2 KB bytes and assign a 4-bit protection code to each block. The PSW program start word contains a 4-bit key. The 360 hardware trapped any attempts by a running process to access memory, whose protecting code different from the PSW key. Since only the operating system could change the protection codes and key, this process will prevent from interfering with one another and with the operating system itself. An alternative solution to both the relocation and protect problem is to equip the machine with two special hard regions, called the base and limit region. When a process is scheduled, the base region is loaded with the address of the start of each partition, and the limit region is loaded with the length of partition. Every memory address generated automatically has a base region contents added to it before being sent to memory. Thus, its base region contains the value 100K. A code 100 instruction is effectively turned into a code 600K to plus instruction, with the instruction itself being modified. Gadgets are also checked against the mid ranges to make sure that they do not attempt to fetch the memory outside the current partition. The hardware protects the base and limit ranges to prevent used programs from modifying them. A disadvantage of this scheme is the need to form an addition and count person on every memory reference. Comparisons can be done fast, but additions are slow due to the carry propagation time used unless special addition circuits are used. The CDC 6600, the world's first supercomputer, used this scheme. The Intel 8088 CPU used for the original IBM PC used a slightly weaker version of this scheme. Base register but no limit register. Few computers use it now.